Now in classical mechanics, no matter what happens, this ball's not going to end up on the other side of this barrier. The only way it could do that is if it went around it or it broke through it. But what's weird is if you shrink everything down to a smaller scale, that's not the case. If that barrier becomes very thin, there becomes a non-zero probability that you'll find the electron on the other side of the barrier without ever having broken the barrier. No matter how impenetrable your barrier is, it doesn't matter because there's always some non-zero probability that a particle is going to end up on the other side of it when you measure it. So the particles that we're going to be using for our experiment are photons. And the impenetrable barrier that we're going to be using is a reflective surface. So when you're past a specific critical angle and you're shining light out of water, what happens is that light doesn't actually leave the water, but it just reflects off the surface and goes back into the water. You can also show this total internal reflection using a laser with water pouring out of a spout. Look how the laser just stays with the water. Notice that as I hold the glass sideways, you can see my fingers easily on the other side of the glass. But when I turn the glass upright, suddenly the sides of the glass become like a mirror. You can't see anything outside of it. So basically this water-glass boundary here is acting like a barrier. It's not letting any light pass through this. So no light is getting from my finger to the outside of the glass up through the camera. You can see it completely blocks my hand here. And what happens in this case, because the air has a lower refractive index than the glass and the water, it means that the probability of finding a photon outside of here exponentially decays to zero quite quickly. So in this case, the boundary is actually the air around the outside of the cup. But it turns out if you can make that boundary small enough, if you can get that layer of air small enough, you actually can see the light. So the photons from my finger can actually quantumly tunnel through that boundary layer of air and get to the camera. So when I touch the glass, you still can't see my fingers. But now watch what happens if I press really hard and try to reduce that air layer in between my finger and the glass to as small as possible. So this is actually a great analog of quantum tunneling. So the only way these photons are getting through this barrier is because I've reduced the barrier of air, to a small enough thickness that the photons actually tunnel right through it. Another way to do this, instead of pressing really hard with your finger, you can reduce that boundary of air in between there just by getting your finger wet. So now my finger's wet, so instead of air in between there, there's water, and the water has around the same index of refraction as the glass and the water, so then you can easily see my finger. So next time you're at a restaurant and you notice that you can only see your fingers on the glass when you're holding it tight, you can start up a nice conversation about quantum mechanics at the table. And thanks for watching, and I'll see you next time.